Hello YouTubers, it's the day you've been waiting for. We're actually going to get some real graphics on the screen. But first we have to go through some initial information. So let's load our source code. And remember to choose the right disk drive. So here's our initial comments, version 1.00. So we're going to use the draw and xdraw shape commands to put something on the screen. We're going to use the keyboard, and eventually we'll have some collision detection. But that won't be in today's tutorial. But what's important to talk about today is breaking our source code into smaller parts. Now, Merlin will crash quite catastrophically if your source code is too large. I don't know what this limit is. I just know that I have come across it a few times. And when it happens, you have no opportunity to save your source code. So keep your sources small. So let's look at the initialization of our game. So we're starting our source code at location 8000 hex, and then we immediately jump to what's called the start of the game. But what is this thing in line 21? The put game equates. Well, the put command inserts source from another file into your game at that point, into your source code at that point. So let's load the game equates. So here's our famous equates that we had in the previous demonstration, our max x, max y, and a few other additional equates that we've probably haven't seen before. Okay, I interrupt this video for an important announcement. I forgot that the Merlin files, which you create in the editor, end in .s. But those are not what are loaded when you do the put statement. They start with t dot, and those files are generated by using the write text file command. So after you've edited each file, for example, if you load the ROM subs and you make a change to this file, you have to quit out of it and say write file, which writes a text file. Type Y, and that writes a new text file to the floppy disk. You have to do that with every file that you use the put statement with. Back to our tutorial. DFB stands for define byte, and it generates the bytes specified by the expression. And you can use several different types of bytes for of data, separated by commas. The standard number format is used, and arithmetic is done as usual. The symbols less than and greater than sign are used to specify the low and high bit of labels if you use that. And if you don't specify a less than or a greater than sign on an address, the low byte is assumed. Okay, so now let's go back to our source code. So on line 20, we jump to game start. And the reason for that is we're actually defining some storage within the equates. And we don't want those being attempted to be executed by accident, so we just jump over that storage. Our next routine on line 24 is to initialize the shape tables. And then we jump to a subroutine to initialize our game variables into a known state. Then we clear the screen, switch to full graphics mode, and draw a border. This is all our initial state. Now, the next part is our main loop. So we draw a car on the screen, we wait for a little bit, we check to see if there's a key. If there was, in that routine, it will set a 1 in the quit address. So the accumulator loads from the quit address. If it's equal to 1, this comparison will not be equal. If it's equal to 0, that means don't quit, and it'll jump back to the main loop. If it is equal to 1, it'll fall through, go and switch to text mode, and exit the program. Now, all our routines that we were calling earlier are in separate modules, separate source codes. So all of these are stored separately, and we'll go into those shortly. But the advantage is you can have a very small main program and be able to test all your routines separately. And once they're tested, you can use them over and over in future games. So you'll see that on line 52 I have the list statement on. That'll allow us to see what's going on when we compile our code, or assemble our code. Now I've stopped time here to show you that the put statement for game equates has inserted the source code from the game equates file into the assembler while it is assembling it. Okay, now if you don't want to see all of that source scrolling by as you assemble it, you can put a list off somewhere near the beginning of your source code, and then it'll be a nice quiet assembly. Okay, now it's time to go through the source code. Let's look at the first put that we have at the end of the program, ROM subroutines. And basically these are the Apple II subroutines that we call. Not all of them are used, but we put them into one routine, one file, and we can reuse them over and over again in the future. So here's our simple routine for clearing the screen, setting full screen, and then setting the color to white. That's what our set screen does. Our initial variable routine sets our current rotation speed, sets where the location where the car is, and says whether or not we've collided or not. It also sets the quit state to 0 so that we don't immediately exit the program if it's some non-zero value. You should be familiar with our border routine. We've gone through it enough times. This is the routine that draws the box in white on the outside of our monitor. Finally, some new code which we haven't seen before. We're going to use the shape table routines that are built into the Apple II ROMs in order to draw a shape on the screen. The first thing we do is we set up the shape table by storing the location where the data is stored. That's done through lines 7 through 10. The next line is to say that we don't want it to be rotated, so we store 0 in the rot location. And lines 13 and 14 set the scale. When set to 1, they are drawn 1 to 1. If you set it to 2, it'll be drawn twice as large as the original. Okay, now we're going to talk about what the actual shape data is. The first byte in the shape table is the number of shapes in the table. So in this case we have 2 shapes, one called car and one called circle. The next byte is not used. The next 2 bytes is the offset from the start of the table where the first shape table is. The next byte is the offset to the second shape table in memory. This can continue on based on the number that is in line 18, the number of shapes you have. Now we get to the really gross part, which is actually how shape tables are done. So I'm going to give you a little brief introduction to this, and then I'm going to tell you the easy way to do it. So hopefully you know some binary. If you don't, it's not a big deal. Now, the value in 24 hex works out in binary as 0010 and 0100, shown in the graphic below. Now, this is important because the shape table instructions take a byte and they break it up into 3 sections. Now, shape table for each byte is broken into 3 sections. Section 1 says whether you should move or plot. Section 2 says whether you should move or plot. And Section 3 you can only move on. So if you look at the data that I have shown, Section 1 says plot, then move up. Section 2 is plot, then move up. The third section, move up. The next byte is plot and move up. The next one is move right, plot and move right. And the next one is move up. The next section is move right and plot and move right, plot and move right, and then move up. So you can see it's kind of a very confusing system for building shapes, and that's why I don't recommend you do them manually. Instead, use the Beagle Brothers shape creation routine. So now I've loaded the draw car source. The first bit of source in here is how to erase a car. So what we do is we set the color to black. We set the location where the car previously was. Make sure that we're using the same scaling that we were using previously and the same rotation. With that, we load the location of the shape that we want to draw, and then we call the XDraw routine. Drawing a car is very similar to racing one, except we have a few more housekeeping things to do. For example, we keep track of the color that we were using when we drew the car. We keep track of its location. We keep track of its scale. And we also keep track of the rotation that we used as well. And doing all of those things, we can also determine if we have collided or not. The draw routine will tell us whether or not something has, if something underneath what we drew was actually there. Okay, the next routine we're going to look into is our keyboard routine, checking to see what keys the user has been pressing and what actions to take when we notice them. So if we look at the source code at the beginning, I have a whole bunch of equates as to what the up key, down key, left, right, etc., upper left key, etc., etc. So these are all equates that we can use to moving the car around. Now, reading the keyboard is pretty straightforward. All we have to do is check to see if the carry flag is set, and if it is, there is a key waiting for us to grab. So once we got the key, we can compare it to see whether or not we're pressed up, down, etc., etc. So everything is pretty straightforward here, except for the quit key. When the quit key is noticed, we store the value 1 in the address that designated by quit. If any of the keys that were pressed were undefined, we just ignore it. The next section simply stores the direction the car should continue to move in once a key has been pressed. Well, now we're finally at a point where we can actually start compiling our whole game, which really is incomplete at this point, but at least it'll display something on the screen. So let's load the main source, type ASM, and compile our source. Apparently I forgot to save my source code when I added the list off statements. Okay, now our source is in memory. We need to save the object code. Press O to save the object code. Quit. And brun main 100. All that code just to display that, but at least we have something on the screen. Our next episode, we'll start moving things around the screen.